tech talk of our Tech for Impact campaign. My name is Jasper Petrich. I'm Director of Alumni Relations and University Fund of the TU Delft, and I'm your host this afternoon. And this afternoon we'll talk about quantum science, and it's my great honor to do this together with Dr. Anasua Chatterjee. Anasua, before we turn to you, I'd like to elaborate a little bit more about what the University Fund is doing and why it's so vital that people are supporting our Tech for Impact campaign. So bear with me a couple minutes. Here at the TU Delft and at the University Fund, we strongly believe that a large and tight-knit TU Delft for Life community is vital for the success of our university. And this vast and tight-knit and active community will be very beneficial for the TU Delft, but mainly for the alumni. And the TU Delft can share their knowledge with the people and they can use it at their work, but also the TU Delft can get the knowledge from the alumni, what they see in the real world. And but mainly it will be fantastic if this vast community will communicate among themselves and be beneficial from one alumni to the other. However, this sounds logical, but can only be successful when the TU Delft remains successful. When the TU Delft remains a top-ranking university, people will be proud and will think about university and be interested in what's happening here. When TU Delft remains a top-ranking university, the alumni will send their children here. And when the TU Delft remains a top-ranking university, it's also interesting for alumni to come back and learn more and give back. But for TU Delft to remain a top-ranking university, we need top-ranking researchers and we need top-ranking research. And unfortunately, top-ranking researchers cost a lot of money, and top-ranking research costs a lot of money. And as we all know, we live in times that there's not so much money as there was before for research. And the whole world of science has become very, very competitive. So researchers need to limit their budgets and have to do more research for less money. And therefore, it's extremely important that the University Fund can help researchers do just this little extra. Because we all know that the truly brilliant things have always been always came from the small projects, the side projects, and you can see a donation to the University Fund and to the projects and research projects that we support as a seed fund, as an incubator for truly brilliant research. So I hope that at the end of our talk and your presentation, that people will really appreciate what they've seen and make a donation, small or large, to your research, because I think it's very, very important that the world will be supporting scientific research, and especially our TU Delft alumni. But also, if you're not an alumni and still watching this, and you feel and Delft has a warm space in your heart, make a small donation. However, we're here today to talk about quantum, and now, Anasua, we come to you. We've met before. You're part of our Accent Fund, and I've heard you talk about quantum. And usually, in these tech talks, I will explain a little bit about the research you're doing. But today, because it's about quantum, and I've heard you before, but I still don't get it, I think it's better that you tell us why it's so important that there is research done in quantum science.
So I would say that, first of all, thank you very much for having me here. I really appreciate all the support from the TU Delft Excellence Fund, which is also an initiative of the alumni. And my area is indeed in quantum science. And to me, it's very interesting because quantum science has really come out in the last decade or 20 years from something very much academic physics into something that people are realizing can have really big impacts on a lot of different fields, just like what we call classical computing, what most people know of as computing, had an incredible impact. A lot of people didn't even imagine the impacts it could have when they were making the first computers. And so with quantum science, the hope is that we can use some of the very basic properties of very, very small, cold, nanoscale systems to actually do computing, but with much more power than before. And I will explain about it a little later.
Luckily, because still, if I hear you talking about it, it's the idea about. I mean, it took me years to understand the zeros and the ones.
Yeah.
Now there's something in between. Fascinating. But Anasua, how do you feel about your project, your research being chosen in our Tech for Impact campaign? I can imagine that now you're a famous person in Delft. How does it feel?
It's been really interesting, actually, because I think a lot of my neighbors and friends and people I know in Delft, not maybe so surprisingly, turn out to be alums of TU Delft.
Very good.
So I have been, people have been talking about the projects, asking me to explain about quantum. It's been really excellent, and I think it's exactly as you say, that this is a kind of seed fund, a thing where you can explore some of your more interesting ideas. And I think this has been really special to me because I could bring out a project that's very dear to my heart, but maybe not so much fundable by like a typical government grant. So I think this is a really excellent campaign because of that.
Can you elaborate a little bit more about the fact that your project is not fundable by government?
Well, I mean, okay, it could potentially be fundable if any government agency is listening to this. But the idea here is that, as I will explain in a bit, quantum is really kind of concentrated in the universities and the research institutes right now. And so there is a need to have, just like with classical computers, to have the citizens and the students and the high schoolers and everybody to get their hands on these systems and to get them to understand what it is about. And so currently we create these chips in our own labs and we measure them in these really, really cold cryostats. Exactly, yes. Which, they cool these systems down to very cold temperatures so that they maintain their computing state. And these chips that we make, again, are not accessible to people outside. And this was also the case with classical computing. Those, those transistors, the chips they made were only accessible to very few people. And so maybe I can show this again later, but, just to show you and the audience that a typical chip will be very small, and on such a chip of this size you can probably have billions of these small computing units. But again, I have stolen this chip out of my lab and it normally doesn't leave. So the idea here is that, a project that is geared towards democratizing quantum science, towards having education, training, all of this is not really maybe so much on the radar of the governments. They want to support just the frontier research.
Yeah.
So this is why this kind of campaign is essential for this.
In fact, by democratizing it, a lot more brilliant students and researchers like you can use it, and from that, it will exponentially grow the knowledge about.
That is exactly the idea. Yes.
Yes, and you talked about the attention of the neighbors, but are you being recognized also now on campus by students? Because your face is on the near the coffee machines. We can see the campaign is advertised there. So.
Well, my own students have been teasing me about it, and I think I have had an uptick in master student applications. So now that you mention it, it could be because of such a thing.
That's good to hear that our campaign works also in the master student uptake in master students. Very good, because it's one of the goals of the university. And it's funny, and I've asked these other scientists as well in our campaign. They're all passionate about what they're doing, but with you almost radiate passion about this subject. Where does it come from? Because it's how do you get in contact with quantum?
It's very interesting, and I could, some people say that there's a lot of societal advancement you could have. Again, like classical computing, you could revolutionize, drug discovery and other things. Mm-hmm. And I can say that, but it would be a small lie, because I think honestly, what really excites me is that I'm by training a physicist, and I find the physics and the complexity of these systems, and also the fact that you can do such intricate computation with single electrons. Mm-hmm. That kind of knowledge is very exciting to me. And of course, it's nice that it may have some good impact in future.
Yes, and so your connection to the hardware, to the real chip,
yes,
is as important as what we can do with quantum science.
Yes, that is right. And, this is why TU Delft is really at the forefront of this research, because the facilities and the chip-making facilities here are really excellent. They are, at the level of some commercial clean rooms, I would say. And so we can make very complex chips. And so this is really one of the biggest reasons that I have made my home here. So,
yeah, because actually that's my next question. Why Delft? How did you get here?
So, I would say the climate of the Netherlands, but it was not this.
Hardly anybody would believe that, I'm afraid.
To me, I think, this kind of research, as you say, it's not only very expensive, but it's also, you really need to be around other excellent people. Mm-hmm. And the Netherlands is really one of the front runners in this field, starting from the days of low temperature physics in Leiden and in Delft. And then going forward to quantum physics, which again, many of the big discoveries were actually made here. I think, and in current years, the field of quantum, both for academic groups and also in terms of startups and other things that employ a lot of our students, this has really expanded. And so I would say most people in the world, when they think about, what would be a really excellent place to go do this research, would think of Delft. So I think that is a really big thing to be proud of.
Is Delft indeed a front runner in this research?
Yes, definitely. And, in terms of papers produced, students, in terms of, the really breakthrough work that it does, I think it's really in the forefront in Europe and the world. So for me, it was definitely one of the top destinations for my science. Yeah.
Oh, anyway, we're really glad to have you here. It fascinates me that that Delft is such a front runner in this field, because you typically expect that the States or China is also in the front, because this is such incredibly important research being done. I mean, I've heard that designing new drugs or improving IE or AI, whatever, it all has to be done with quantum.
Yeah, so I think this is, of course, a reason why, indeed, in the US and China, also Australia, the UK, all of these countries are now having their national quantum initiative, also the Netherlands. And so I think, indeed, all countries around the world are working on this. Delft has, or the Netherlands has also a special connection with low temperature physics and semiconductor physics. Mm-hmm. I mean, also there is in ASML, there is, and this kind of chip making is also also very much in the DNA of Europe. There are so many really good chip makers in Europe. So I think this is just a very magic conjunction of all of this coming together.
Yeah.
But just as you say that all of these other countries, indeed, they're putting a lot of funding into this field. And so, indeed, to stay at the forefront, we need to maintain the momentum. So that's definitely true.
So we need extra funding. That's very important that we all realize that what we're doing here in Delft is extremely important.
Yes.
And it will never go without extra funding.
Yeah.
And other countries are throwing money at it.
Yeah.
So we need to do the same.
Yeah.
To remain in the
Yes.
in the front.
It's definitely a race. It's a friendly race because it's a very exciting technology, but it's a race between different countries.
Yes. Anasua, I think we can't wait any longer. And please take the floor. I've seen they improved it a little bit for you. In the meantime, let me tell the audience that if you want to ask questions to Anasua, you can do it in the application. So in the call, and I will see them here on my screen and ask them later. We also are videotaping this, so you can look it back, and I presume people will do this many times because it's so interesting what you're going to tell us. Good luck. The floor is yours.
Great. Hello, everybody. I'm Anasua Chatterjee, and as we've said, I'm an assistant professor at the Quantum Institute QTech and the Kavli Institute of Nanoscience at TU Delft. And what I want to tell you today is very high tech, but I want to start today by a very, what you would think, low tech slide. And this is not something I have to explain to the Dutch people, but when people were navigating on the high seas, they would typically use celestial navigation. And this was really difficult. There were a lot of difficult computations involved. For example, one of the things you would do is you would look at the lunar distance, and you could do a lot of trigonometric and other calculations to figure out where you were on the world. And to do this, typically there would be these almanacs published with all the tables of, the different functions, and these would be updated every year. And this was actually very hard calculations that people had to do. So because of this, there were people who were trying to find out ways of doing these complicated calculations easily. Among them was Charles Babbage, who made this what he called a calculation machine, a difference engine. And it would calculate these polynomial functions for making these tables, which were useful for military, for navigation, and other things. And actually, the government of the UK funded him. And at some point, he stopped and started working on something else, and they were not very happy. This is how funding typically goes. But he came out with this difference engine, which this is a replica that they had made at the Science Museum. And what it did was it could calculate these tables. And Ada Byron, or the Countess of Lovelace, she actually was one of the first, wrote some of the first programs. And she noticed and wrote down that such a machine not only could count tables, as Babbage had designed it to, but could actually perhaps be used to do more general problems. Many years later, around the times of the World War II, as we all know from the movie Enigma, perhaps, Alan Turing in England also made a Turing machine. And this is a prototype from much later. But the idea here was that a universal machine that could do computation without a human being involved. And here, the idea was essentially to move a tape back and forth and do these computations. And after that, of course, different machines started to come up. So there were the Attensoft-Berry computer, and then on the other side you can see this add-subtract module, which uses such a big amount of space only to do some addition, subtraction. Then there was the ENIAC system, which was used to make general problems easier. And in all of this big systems, you can see that they were not really maybe useful for personal computing. But at some point, people started putting them on a chip. And what happened was that once you start putting these on a chip, you can put many of them on a chip. There's a concept called Moore's law, which says that the number of transistors keeps doubling. And today, because of all these advances, you have an object in your pocket with 20 billion of these transistors, which can switch on and off and go between 0 and 1 and do classical computing. And I would say that these people who are making these different engines to make tables easier could not really have predicted what we would be doing today, that you would be listening to me on a personal computer. So we know that these systems are basically connected grids of these 0, 1, 0, 1 switching objects. And in the 20th century, people started realizing that if instead of a simple 0, 1 switch, you could use something like an electron. So a single electron, it can be aligned in an up direction or in a down direction, which can be a 0 or a 1. But it can also be anywhere on this kind of sphere and have a complex number that describes where it is. Not only that, but if you have two electrons on this grid and they have interacted at some point, even if they are separated, if you measure one, you also measure the other. So if you make a grid of these systems, they have these complex interactions in them, and now instead of this simple 0-1 structure, you have this very complex computational space which can do a lot of problems much faster. So one of the questions you may ask is why? And this is a big question, of course, and to do that we go a little bit into complexity theory. It's not too much for the alumni engineers of Delft. So when these computers started coming out, people started classifying algorithms to do common tasks into their complexity. Some algorithms, if you increase the size of the problem, they don't go up very fast. They, for instance, still remain tractable. For instance, one of these problems is the shortest path problem, which Google Maps on your phone solves if you say, I want to get from place A to place B. And these we say are in P. It's a class of these problems. However, there's another class, which is a very hard class, that's why I've marked it as red, which has a similar problem, the traveling salesman problem. If you're a traveling salesman and you're selling washing machines or something, and you want to go to X number of cities, and you want to find a path L, that's actually a very hard problem. But it has many applications in shipping and many other ways. There's also a different set of problems which people don't know if they're extremely hard or not, but they don't seem to be easy. For example, if I give you two graphs, are these graphs the same? Not an easy problem. And also an important problem, if I tell you the number 15 and tell you to factor it, then you may easily come up with 3 and 5, which is something you may have learned as a child. But if I ask you, what is the prime factor of 30607? This is actually a very hard problem. It would take you a lot of time to test all the factors to do that. So these problems that seem to grow almost exponentially are not very well solvable. And you may say, okay, why should I care about this, Anasua? Well, the prime factoring problem forms one of the bases of modern cryptography. The RSA algorithm, which is how a lot of our private information, our banking, our passwords are stored and hashed, is actually based on prime factoring very, very large numbers. Normally, this is so hard that it would take a hacker, the age of the known universe to do. However, in 1994, Peter Shor he was at Bell Labs then, now he's at MIT, came up with this algorithm, which was a bit of a bombshell. It showed that given, if you use this quantum states, for example, an electron or many electrons arranged in a grid and make them interact, then you can solve this problem not in exponential time, but in polynomial time. So much, much shorter, and it will not expand as the number gets larger. So this was a bit, it blew people's minds, because now you had a completely new complexity class, a class which was solving many problems which were thought to be very, very hard and not really solvable on small computers. So this is really, in just like the Turing machine or the difference engine was, it takes you to a completely different level or a different paradigm of being able to do computing. That's why this has been really one of the biggest, I would say, really exciting problems of the last few decades. And now, you can say, okay, is that it? But it's actually not. So one of the things you can also use quantum computers for is potentially material design. So if you think about nature, then the atoms and molecules, they are also made up of electrons, and they also obey nature's rules, which is quantum. And so you could make superconductors that work at room temperatures maybe, and then superconductors float on magnetic systems, and so you could have a train that levitates on magnetic rails, or you could have undersea cables which carry current without any dissipation, so low loss. You could also think about designing chemicals using such a system. Currently, about 3% of global energy use goes towards the Haber-Bosch process, which is used to make ammonia for fertilizers. But if you could design this molecule better, then you don't need these high temperature and pressure conditions. The other thing you can do is, you can break RSA encryption, but because of what I told you, that two electrons once entangled, if you measure one, you immediately collapse the other one. This is one of the really spooky action at a distance things about quantum. Now, if you are Alice and you send a qubit to Bob, and somebody eavesdrops on it, they will collapse it, and then yours will collapse as well. And as a result, you will know that somebody has eavesdropped on your secure channel. So in some sense, it again gives you this paradigm change of cryptography, which is that you can never have unsecure communication, because you know when it is unsecure. So this was actually used recently by the lab of Ronald Hansen at QTech to show a rudimentary quantum link between Dutch cities. And just to show you a little slide about the QTech Institute of TU Delft, as I said, QTech is really at the forefront of this kind of world-class research. And at QTech, we build these scalable prototypes for a quantum computer, a quantum internet, and we have a lot of people working with this at TU Delft. And it's not just us, of course. There are governments, companies, startups, IBM, big player in the classical computer, Google. They're all also working on the quantum computer. Governments, just like they funded Babbage, are funding us in making these new world computers. And of course, there are many startups, just like Apple was a startup then, some of them based at Delft, who are actually making lots of different kinds of quantum computers and hardware for quantum computers. So, my Tech for Impact question now is, how can we accelerate the quantum revolution? And the answer may not be what you expect, so let's get into that. So as I said, what people did with classical computing is make these grids of 0, 1, 0, 1 systems and scale them bigger and bigger to 20 billion. For quantum, we kind of have to do the same. We have to make these grids of, let's say, trapped electrons that interact with each other. We have to have control over them. And this is what I do in my lab, for instance. So we build these chips like the one I showed you. If you take a cross-section of the chip and look at it from the side, then what this has is a sea of electrons which has been engineered. Now we put some metallic gates or metals on top, and we apply a negative voltage. Now these electrons are kind of stuck in puddles. I will now show you a top view of this image. So if you look at that, you see that on the left side, there is a little gap in the middle where we have pushed out all the electrons. Now we pull back a little on that, and on the right side you see that one electron has hopped back in. This electron can now be manipulated to form the quantum bit. So it can go 0 or 1 or on this sphere and interact with other spheres. Now, if you look at this, you may say, okay, this is very complicated, and it is. The simple system looks like this, and the complicated system, but still only having 4 qubits, looks like this. Not only that, but this system has to be taken and put inside something called a dilution refrigerator. It is a refrigerator which goes 100 times colder than outer space. If you look at it, the picture looks very, I would say, almost steampunk, but basically it's a lot of lines coming from room temperature down to your chip so you can control it. So each of those wires is basically a control line. And the reason is you need your system to be very, very cold so that your electron is not moved around by something else. After all, it's a single electron. So if you look at this, you can see that this is a very complex system, and it's hard for students or the general public to interact with. And now, to tell you about my project, we have to go again back to the old classical computer. To be specific, the Apple I. So this is a prototype computer from the first product of Apple, which we all know very well. And Steve Wozniak actually, he sold, I think, his calculator, and Steve Jobs sold his Volkswagen car to make such a system. He made around, I think, 100 of them. And the first thing he did was he actually donated and gave away a few of them. In fact, the first unit was used in a high school math class. So why did he do this, right? Well, maybe some of the civil engineers or others can think, why does AutoCAD donate their software to our students? The reason is that students are really the lifeblood of adoption of any technology. Just like the Apple I, people took this system, they took other very new software like BASIC and Logo coming out of Microsoft and other places. And they built, for instance, their own wooden housing that you can see in the picture around this little printed circuit board, and experimented with these computers. A lot of them grew up to make the first startup companies. If you look at universities of the time, Drexel University, for instance, made every incoming student have a personal computer. A lot of them were also donated from these new companies. So the main message here is we need to get it into the students' hands. And I would say that this is in some sense the mission of QTech, also the mission of the QTech Academy. This is we make videos, we make a lot of Quantum 101 topics. This is a video of Professor Menno Veldhorst. The QTech Academy is currently run by Dr. Christian Andersen. And the mission here is to get students interested in the system. In other universities, such as the University of Copenhagen, where I was previously, we have been able to have a quantum training laboratory funded, where students can come in, they can work on these little dilution refrigerators, they can have chips, and they can work on these systems and get to know it. So to end my presentation, answer my question, how can we accelerate the quantum revolution? In my opinion, the answer is, of course, by doing excellent research and advancing the field, but also by getting quantum chips into the hands of students. And thank you very much for your attention.
Thank you. Asha, come back. Fantastic. Of course, I've heard your story before, and still, I always wondering when you tell about the electron can be either facing upward or downward, or that in between phase. You say a very intricate number can describe it. So, and it's always another number, but it is a number.
Right. So I think in some sense it's a bit counterintuitive, but in this sense, I would say the force of gravity is also counterintuitive when you first hear about it. We kind of accept some things from first principles. And here, I think, when I was learning about quantum physics, there was this, it was literally called, this shut up and calculate method. So the idea is that you teach students that this is the only theory we have where the math, the linear algebra, works out so well that it can describe almost all of nature's phenomena. And so in some sense, most physicists of the early 20th century had no chance or no choice but to accept that this was the best description of nature. Even Einstein had trouble with it, right? So then it's true that an electron, if you put a magnetic field, it can be aligned and it can be anti-aligned, but it can also be in a superposition of aligned and anti-aligned in a complex number. And even more crazy than that is this idea that even if you separate the two of them, they know somehow that,
this is something I've no idea how this can, but we just have to accept it's been proven.
But that's where I am as well, that we have to accept it.
It's what it is. Of course, a lot of questions came in, and I can imagine why, because this is so much at the forefront of science, and we've had scientists here before, and of course it's fantastic what they're doing, but I can have a grasp of what they're doing. But the idea of this one electron doing the same as the electron miles away is something that nobody understands. So there are a lot of questions, and I'm wondering which one to ask first. But I thought, as a parent myself, I was very intrigued by the question of Erik van der Meij, and he said, "When will my daughter's life, and she's now 8, be influenced directly or indirectly by quantum technology?" I thought that was it's an interesting question.
It's an excellent question. So the first thing I would say is, if you ask my father, he would say my life has already been affected by quantum technology very, very much. So I would encourage your daughter to join us and do research in this field. But there's a serious answer in there, which is that in the beginning, it will not be that these systems are, in everybody's hands, but they will be more like these mainframe computers at the beginning, where the universities and the defense institutions and companies like IBM and Google will have their own versions of these computers. And when you want to do a complicated calculation, for example, the inner structure of an atom, which maybe your daughter will be doing when she's in college, then you can log into this computer and do this part of that calculation on a quantum computer. So I would say that just like these first classical computers were used for research into the thermonuclear bomb. They were used into research into making these, tables more accurate. They will first be used for scientific research. So I think that those applications are already here. People are doing this research using, for instance, IBM small computers. But for a commercial use of these systems, again, I know as much as the next person.
But already, I've seen the cryostats at QTech, and people are making calculations.
Yes.
So already people are using it to calculate something, and
So it is true. However, I would say a lot of the things that people can do today would fall maybe into the category more of quantum simulation or studying quantum systems, because the biggest thing about these systems that I have not talked about in my talk is that they are prone to error. And just like the cryptography or the information is protected in these systems, they are also vulnerable to loss. Because if you don't keep them cold enough, if you don't keep them isolated enough, then the information will decay. And so this is something that is the biggest roadblock for these systems. And so, this will take time, and even if people make many, many qubits, you still have to make them low noise. So this is actually now on the roadmap of IBM and Google. And
because there was also a question from one of the viewers, Krishna Sampatakumar. She says, is it is it better to build a connected qubit system, or do you see advantages in moving forward a qubit-based system?
I mean, it's a very technical question.
Yeah. You were talking about
That's true.
stacking them, or
That's true. So I think when people are saying that if you make a qubit, then instead of up or down, you have a kind of sphere of possibilities, to be very colloquial. If you have a qubit, then you increase the inner space of computation even more, to put it in layman's terms. People are researching this. On the plus side, yes, of course, you increase computational power. On the minus side, they seem to be much harder to make. There are companies working on them. I honestly think, the first pictures I showed of the computers, they use these vacuum tubes. Yeah. Today's computers don't use vacuum tubes. So I think we will first get to a point with some system, then some other system will be better, and it will be a give and take until you find the best thing for the best purpose.
Do you think in the future there will be computers that can work on room temperature and not in the cryostat?
So there already are certain systems which work at, so the systems I work on, some of them work at, let's say, slightly warmer temperatures, like 1 Kelvin instead of 0.00.
Oh yeah, that's
Kelvin.
warm.
Yeah. There are systems which can show quantum behavior at room temperature, but they are very hard to control because the reason they can show this behavior is because they're very well protected, maybe inside an atom or something. And so there's always pluses and minuses, just like vacuum tubes and transistors.
Yeah, but before you have a cryostat in your pocket, it'll be some time.
That I think we won't have indeed. Right now, though, they are tabletop sized. So,
yes?
Yeah.
It's interesting. And another question, also from a viewer, is Dr. Redert, and also a little bit of a technical question, but I think these technical questions are interesting for the. I mean, we have a audience of Delftenaren.
Yes.
They understand.
Best engineers.
They understand this stuff. Dr. Redert asks, is there a limit to scaling of quantum systems? Is that considered in your work?
Yeah, what can I say? We are full of limits. So I will answer, I think, to the two questions that are hidden in there. One is that currently there are many limits on scaling. The first being that on a single chip, you can only fit so many qubits. Even if you fit the qubits, I showed these metal gates that we control them with. Those have to be fanned out to the real world, and that makes a lot of control lines. This is a big control problem. So that's a limit. The second thing is that applying all these voltages to these systems becomes also a big control problem. For a classical computer, you have to do an operation that is 1010, switch on, switch off. For a quantum computer, you have to make an operation that says where on this sphere you want to put it. That is a much more complex quantum control problem. So these are all limits in one sense to scaling. Of course, also in a cryostat, you can only fit so many chips. That's again a limit. So the other sense in which you may mean limit is there a kind of physics limit to such a system? That I don't think there is. This is a very actually foundational quantum question. How big a thing can be entangled at one time? It's actually not known, but TU Delft, Leiden, and some other universities have formed a consortium. It's called the quantum limits. So it's a very good question. They are now investigating these questions. So.
If there is.
Yes, exactly.
Interesting. We have also a question asked before by Sander Kappinga. And he asks, what are the challenges in quantum computing in terms of hardware and software? Well,
yes.
And then I think the software part is interesting because hardware we more or less covered.
That's right. So hardware indeed we covered quite a bit, though you can still say that a lot of the hardware complications can also be that there are a lot of them, different types of things. Some of them are made by companies, some by research labs, some universities, some by other countries we may not trade with. So there are a lot of barriers to figuring out even what is the best hardware. Software, it's again very interesting that there are not really very clear standardized software. So, for instance, at QTech, we make our own kind of software. We have a team that works on this. In other universities, they may have their own software as well. So it's a very kind of fragmented software platform. So this is really important that people work on this, but it's, for now, I would say, another big problem. People have to talk to each other. They have to make a common standard.
Yes. Well, it's and in order as people in your project need to work with the quantum computers.
Yes.
If everybody talks the same language,
yes,
we go a little bit more.
That's
fast.
right.
Yes. And another question, and of course, this is we could expect this question, and it's been asked by Remco Helwerda and Stephanie Wiegers. Is it possible to use quantum computer to train AI models in a more efficient way than the current methods used by GPUs?
Yeah. So for certain problems, it seems that the answer is yes, but the problems where it seems that it might be useful are also quantum problems. So for example, for if you want to use AI to figure out, let's say, I don't know, protein folding or like the internal structure of molecules or things like this, then you may gain a lot by the input can be quantum states that you have designed in a particular way. But if you ask, for instance, about financial markets and whether this is useful for quantum and AI financial markets, there are a lot of very smart algorithms and theorists, engineers working on this. So this is, I would say, one of the most researched areas because of its big impact.
Of course.
So I don't think, in my opinion, there is not a killer application yet in this area. So to me, the applications right now are in actually science and technology of quantum-enhanced AI. But this is, again, I'm not the world expert on this. I'm the lowly physicist who makes the systems.
Well, you are the expert in this room. Believe me. A question from Mr. Niesen. What's currently the most blocking problem? It's always good to know,
Yes.
what's blocking the
Yeah, so I would say
progress.
In my opinion, the most blocking problem is this the problem of error correction. Like I said before, these systems are, most of them have to be kept very cold. They are very prone to error. The environment can measure it and collapse the state. And so, in a normal classical system, it can also be prone to error. But the big power we have there is that, let's say you want something to record 1, you can record 10 bits that all record 1, 1, 1, 1, 1. So you can store the information in a redundant way. For a quantum system, you cannot, because you cannot fundamentally clone or copy a quantum system. It's literally called the no cloning theorem. So if you cannot copy a thing, how can you keep it safe, right? You have a picture, you want it not burn down, you make a copy of it, but you cannot. So error correction or fixing errors has to be very, very complex. And so this is something, again, that's a area of work. Google has recently released a chip where they have shown for the first time that error-corrected bunch of qubits has performed better than one of those physical qubits. So there is progress being made, but I consider that if we can show that we can correct the errors, then we can scale and we can have quantum computer much sooner.
Because to understand this correctly, you say the chip sort of the qubit can collapse after,
Yes.
and then everything is lost. So
Yeah, exactly. Like, let's say you have encoded some specific state that you want to find the lowest energy of in a system of 1,000 qubits. And let's say for some reason they're all entangled. If you measure one, you will collapse the states of the whole system.
Yeah.
And the environment can interact with it and measure it. So you have to protect all of these qubits, but you also have to detect if an error has happened.
yes.
So this is all very difficult and much more difficult than for a quantum computer.
For a normal
For a classical computer.
yeah.
Exactly.
We have also a question from Bardia, and I like this question. it is many students are worried about the limited job opportunities in quantum. I had no idea that this worry existed, but I'm sure Bardia knows what he's talking about. What makes it still worth pursuing, and what should motivate us to take that risk and go into quantum?
Yeah. So I would actually say that right now it is not a very limited field. So most students I graduate are snapped up, like, even before they have graduated. It's been the case for most of my students. I think what you may mean is maybe in future you anticipate that this may happen. Mm-hmm. And this is a worry definitely also of mine, because, TU Delft and the University of Copenhagen and other universities have started, master's program in this, and students will graduate with a degree in quantum information. And so you may think, in 20 years, what if this field doesn't work out, right? So to me, there are two answers. First of all, I think given the proliferation of these companies and these, big actors like IBM, Google, taking an NVIDIA now, taking an interest in this, I think job opportunities for now are probably not going to go down. And I would also say that, if you say, okay, then what about later? As a physicist, I would say, I'm not very employable either, If you have a degree in applied physics, in some sense, you're also studying something that people might say, okay, well, what are your job opportunities, right? Yeah. So these students we are educating are actually very skilled in problem solving, in physics, in math, lots of very hard sciences. So I don't think that studying this will limit their opportunities. No. Because, okay, I'm not a good example because I'm an academic, but,
I'm sure when Delft makes the big mistake of letting you go, that there are thousands of universities here at the gate calling your name. And another, actually, maybe a bit more political question is asked by Dries de Groot. Mm-hmm. He asked, are inventions held back by Google or other companies, so they have to be reinvented by us because these companies do not want to share it?
So I have lots of, just to caveat, a cliche caveat, that I have lots of friends working at Google and IBM, and I deeply respect the work these companies are doing. In my personal opinion, I think yes. I think it's unavoidable also by these companies because, of course, they have the profit motive, and their patents are the protection of their investment in some sense. I do agree that having these companies be at the forefront, developing things, a lot of this stuff they do publish, but of course a lot of the nitty-gritty of it they don't publish. And this is indeed really excellent people who are working here, but maybe they're not publishing everything. So it will probably set back the field and is setting it back in some ways. On the other hand, the field is moving much faster because of the interest of these companies. So what I would really say is that to counter this, the universities and the governments need to fund publicly funded science that develops all of this knowledge and protects it in the public domain. Yeah. This is something I really care about, this open science. So I think the EU does an excellent job of this.
Good. Yeah, and when they're not funding it, I hope that the people that watch you today will.
That's exactly.
Take the responsibility and think this is important.
Yes.
Yeah, we need to. This is, as you say, it's a race, and it's a friendly race, but it still is a race. And
that's right.
And as you also explained, the impact of being able to control quantum mechanics and quantum computing gives you a huge advantage.
That's right.
So it is, I think, important to be at the forefront.
Yes.
And other question that has more to do with the surroundings of quantum computing is Wessel Bakker's question. He asked, the boom in AI computing required data centers that are putting an increasing burden on power systems and are using a lot of energy, yes. Which you can question if that's very sustainable. And what's your breakthrough of quantum technology? Is this going to solve it, or does it make it worse? Because the cryostat doesn't run on air.
No, that's right. So I agree with you. Okay, I would say that the running of the cryostats, in some sense is probably not that energy intensive. They are still vanishingly few in the world. And I would say that could be offset by if, for instance, as you say, if quantum can enhance the training of AI by providing better quality data or better simulations even of scientific systems, then this would prevent the power required to train the AI by classical methods. So that could be a saving anyway. I do agree that the problems that we choose to solve with these systems should be well defined. We shouldn't just throw it at anything to see what sticks, but they should be informed by proper science and understanding what problems they're suited to, just like AI. So
yeah,
I think this is in some sense a kind of political or regulatory question. And it's interesting because right now there isn't really that much regulation or even understanding of what should be regulated, just like there aren't standards. And so this, I think, is indeed in the next few years, a lot of governments are really looking into this. But one has to be very careful not to stifle innovation as well. So.
Absolutely, yeah, and that's of course the danger. And I can imagine that there are few legislative people around that have some inclination of what's going on.
Yes. We do have, visits from people in government at most of the institutions I've worked at, but this is a very slow process while the research goes very fast. So
yeah, I can imagine, and they might see they go home after they visit you and said, I've been to the coolest place in the universe, which is true.
Yes.
But or near it.
Yes.
But have hardly any idea of what's going on.
Right.
So it's I can also see the challenge of coming up with legislation for this. Rick, I don't know his last name, has asked another little bit more technical question, and I think it's nice to end our conversation with a technical question. We are in Delft, so it's good. And from his basic understanding, measuring anything in quantum state changes the state of the object. Even I knew this.
Yes.
But how can you measure a qubit correctly?
Yeah. So I think it's a conflation of a few different things. So basically, when we say that measuring something changes its state, what we mean is that when you have, let's say, an electron, and we say it can be anywhere on the sphere, your measurement can only be, let's say you have a magnetic field, and you can only measure is it aligned or not aligned with that magnetic field. So even though you can be in, anywhere on the sphere, you can only measure is it up or down. So to do the measurement, you can do computation anywhere on the sphere, but you have to at the end project it on this line in the middle. And so that's what I think the question means. To measure a qubit correctly, you have to project it, you have to collapse it onto the 1 or 0 axis and then measure it. So this doesn't really kill your quantum computation because the algorithm you have written takes into account that at the end you will have to collapse all the qubits to measure them. So this is something that the algorithms take into account, that you initialize all the qubits also in the 1 and 0, then you let them evolve in their own spheres. At the end you again collapse them, and you just have to write your algorithm cleverly.
Anasua, I wish I understood what you were saying. Anyway,
you have to calculate.
Yes, we have to. Yeah, that's. Anyway, Anasua, I want to thank you tremendously for your time, for your very interesting talk, and for the people at home. I hope that. Seeing Anasua and hearing about this quantum research, you realize it is such an important research, not only for Delft, but actually for the Netherlands and for the world. So please help us help us help Anasua and make a small donation to the University Fund and to our Tech for Impact campaign. This was my third Tech Talk and by far the most complicating. And I hope to see you next time. And I wish everybody a very good night and till next time. Goodbye.